Manufacturers may use substandard grounding connections for a few reasons. Firstly, cost-cutting measures. Manufacturers may prioritize profitability over safety by using cheaper materials and designs. Secondly, lack of industry standards. While some general grounding guidelines exist, there are often no specific regulations or standards for grounding in certain industrial applications. Thirdly, lack of enforcement. Authorities may not have the resources or expertise to thoroughly inspect and enforce grounding compliance. Fourthly, limited knowledge. Some manufacturers may have limited understanding of the importance of proper grounding and its potential consequences. Fifthly, customer negligence. Customers may not pay enough attention to grounding details or may accept lower standards due to budget constraints or time pressures. When evaluating a specific MCC ground, several concerns may arise. An 8-32 screw may be used, which is too small for a 250 amp connection. At least a 10-32 screw or larger should be used. The connection surface may be painted. Paint creates an insulating layer that can impede electrical contact. Dissimilar metals, such as a galvanized screw and a copper lug, may be used. This can lead to corrosion and deterioration of the connection. Sharp edges and a narrow auxiliary gutter may be present. These make it difficult to bend and install cables properly, increasing the risk of damage or poor connections. Substandard grounding can lead to several consequences, including ground faults and electrical fires, reduced equipment lifespan, potential harm to personnel, and increased liability for manufacturers and end users. To mitigate these risks, several strategies can be implemented. Firstly, educate customers. Raise awareness about the importance of proper grounding and the potential dangers of substandard connections. Secondly, demand higher standards. Insist on products that meet or exceed industry best practices for grounding. Thirdly, inspect and test thoroughly. Perform visual inspections and electrical tests to ensure grounding connections are secure and meet specifications. Fourthly, contact manufacturers. Report any concerns or observed deficiencies to the manufacturers and request corrective action. Finally, enforce compliance. Relevant authorities should strengthen enforcement efforts to ensure compliance with safety regulations and industry standards. Grounding is a critical aspect of electrical safety and equipment reliability. It provides a path for fault current to flow back to the source, allowing overcurrent protection devices to operate and clear the fault. A properly grounded system minimizes the risk of electrical shock, fire, and equipment damage. Grounding ensures that all non-current carrying metal parts of an electrical system are at or near ground potential. This includes equipment enclosures, conduit, and other metal structures. This reduces the voltage difference between these parts and the earth, minimizing the risk of electric shock if a person comes into contact with them. Grounding provides a low impedance path for fault current to flow back to the source. This allows overcurrent protection devices, such as circuit breakers and fuses, to quickly detect and interrupt the fault current, preventing damage to equipment and reducing the risk of fire. Without proper grounding, fault current may take unintended paths such as through building structures or people, causing significant damage or injury. Grounding helps to reduce electrical noise and interference in sensitive electronic equipment. By providing a common reference point, grounding minimizes voltage fluctuations and unwanted signals that can disrupt equipment operation. There are several types of grounding systems commonly used in electrical installations. The specific type of system used depends on the application and the local electrical codes. A solidly grounded system is one in which the neutral point of the power source is directly connected to ground. This provides a very low impedance path for fault current to flow, ensuring rapid operation of overcurrent protection devices. Solidly grounded systems are commonly used in industrial and commercial applications. A resistance-grounded system uses a resistor to limit the amount of fault current that can flow to ground. This reduces the stress on equipment and minimizes the risk of arc flash. Resistance-grounded systems are often used in applications where continuous operation is critical, such as hospitals and data centers. An impedance-grounded system uses an impedance, such as an inductor, to limit fault current. This provides a balance between limiting fault current and providing sufficient current to operate over current protection devices. Impedance-grounded systems are sometimes used in applications where both safety and reliability are important. An ungrounded system does not have a direct connection to ground. While this may seem counterintuitive, ungrounded systems can offer some advantages in certain applications. In an ungrounded system, a single ground fault will not cause an immediate outage. This can be beneficial in applications where continuous operation is critical. However, an ungrounded system is more susceptible to transient overvoltages which can damage equipment. Also, a second ground fault on a different phase will create a short circuit, causing an outage. Grounding conductors are used to connect non-current carrying metal parts of an electrical system to the grounding electrode. These conductors provide a path for fault current to flow back to the source. Grounding electrode conductors connect the grounding electrode to the neutral point of the power source or to the equipment grounding bus. Equipment grounding conductors connect equipment enclosures, conduit, and other metal structures to the grounding electrode. Grounding electrodes are used to provide a connection to the earth. These electrodes can be in the form of ground rods, ground plates, or underground metallic water pipes. Ground rods are typically made of copper or copper-clad steel and are driven into the ground. Ground plates are made of copper or other conductive material and are buried in the ground. Underground metallic water pipes can be used as grounding electrodes if they meet certain requirements. Proper installation and maintenance of grounding systems are essential to ensure their effectiveness. Grounding connections should be tight and corrosion-free. Grounding conductors should be properly sized and protected from damage. Grounding electrodes should be installed in accordance with local electrical codes. Regular inspection and testing of grounding systems are recommended to identify and correct any problems. Visual inspections can identify loose connections, corrosion, and damaged conductors. Electrical tests can verify the integrity of the grounding system and ensure that it is providing a low impedance path for fault current. A ground resistance test measures the resistance between the grounding electrode and the earth. A low resistance value indicates a good connection to ground. A ground impedance test measures the impedance of the grounding system at different frequencies. This test can help to identify problems with the grounding system that may not be apparent from a ground resistance test. In addition to complying with local electrical codes, there are several industry standards that provide guidance on grounding practices. The National Electrical Code, or NEC, is a widely adopted standard that provides comprehensive requirements for electrical installations, including grounding. The Institute of Electrical and Electronics Engineers, or IEE, publishes several standards related to grounding, including IEE 142, Recommended Practice for Grounding of Industrial and Commercial Power Systems. These standards provide detailed guidance on the design, installation, and maintenance of grounding systems. Proper grounding is essential for the safety of personnel and the reliable operation of electrical equipment. By understanding the principles of grounding and following industry best practices, you can help to ensure that your electrical system is properly grounded. Some specific grounding requirements that should be taken into account. Firstly, the size of the grounding conductor must be adequate for the fault current. Secondly, grounding conductors must be protected from physical damage. Thirdly, grounding connections must be tight and corrosion-free. Fourthly, grounding electrodes must be installed in accordance with local electrical codes. Fifthly, grounding systems must be regularly inspected and tested. The use of substandard grounding connections can have serious consequences. Substandard connections may not be able to carry the full fault current, which can lead to overheating and fire. Substandard connections can also increase the risk of electric shock. In addition, substandard connections can cause equipment to malfunction or fail. It is important to use high-quality grounding connections and to ensure that they are properly installed. When selecting grounding connections, be sure to choose connections that are rated for the application. The connection should also be made of a corrosion-resistant material. When installing grounding connections, be sure to follow the manufacturer's instructions. The connections should be tight and secure. Also, avoid damaging the grounding conductors during installation. Regular inspection and maintenance of grounding systems is essential to ensure their effectiveness. Grounding connections should be inspected for loose connections, corrosion, and damage. Grounding conductors should be inspected for damage and proper support. Grounding electrodes should be inspected for corrosion and proper depth. Any problems that are found should be corrected immediately. By following these guidelines, you can help to ensure that your electrical system is properly grounded. Proper grounding is essential for the safety of personnel and the reliable operation of electrical equipment. The NEC provides specific requirements for grounding electrode systems. These requirements are found in Article 250 of the NEC. According to the NEC, a grounding electrode system must consist of one or more of the following electrodes. Firstly, a metal underground water pipe. Secondly, a metal frame of a building or structure. Thirdly, a concrete encased electrode. Fourthly, a ground ring. Fifthly, rod and pipe electrodes. For a metal underground water pipe to be used as a grounding electrode, it must be in direct contact with the earth for at least 10 feet. It must also be electrically continuous. A metal frame of a building or structure can be used as a grounding electrode if it is connected to the earth. A concrete encased electrode must be at least 20 feet long and must be encased in at least 2 inches of concrete. A ground ring must be at least 20 feet long and must be buried at least 2.5 feet below the surface of the earth. Rod and pipe electrodes must be at least 8 feet long and must be driven into the earth at least 8 feet apart. The NEC also specifies the minimum size of the grounding electrode conductor. The size of the grounding electrode conductor is based on the size of the service entrance conductors. It is important to consult the NEC for the specific requirements for grounding electrode systems. Proper grounding is essential for the safety of personnel and the reliable operation of electrical equipment. The auxiliary gutter is a sheet metal enclosure used to supplement wiring spaces at meter centers, distribution centers, switchgear, and similar points of wiring systems. Auxiliary gutters are designed to enclose conductors but are not intended to be used as raceways for branch circuits, feeders, or service conductors. The NEC provides requirements for the installation of auxiliary gutters in Article 366. Auxiliary gutters must be securely fastened to the surface on which they are mounted. The covers of auxiliary gutters must be securely fastened. Conductors in auxiliary gutters must be supported. Auxiliary gutters must be accessible. The size of the conductors in an auxiliary gutter must not exceed the ampacity of the gutter. Auxiliary gutters must not be used as raceways for branch circuits, feeders, or service conductors. Auxiliary gutters are often used to provide additional wiring space for large conductors. They can also be used to protect conductors from physical damage. Auxiliary gutters must be installed in accordance with the NEC and the manufacturer's instructions. The proper installation of auxiliary gutters is essential for the safety of personnel and the reliable operation of electrical equipment.